So it's time to teach you a little bit about calculations related to phase changes. And if you look over here at this problem set that I'm going to use for an example, we see that I have the three formulas that we had developed on a previous video that I made for you. That's the video I'm talking about there is the video where I used this graph to talk about the origin of the formulas that we use to calculate phase changes. So let's go ahead and get started. You can see here I have the Q is equal to M times C times delta T on this problem set. I used C subscript P for this. Other than that, it's the same. Q for a phase change is equal to N times the heat of fusion, or the heat of vaporization when you're boiling. This is for melting, and I'll show you how to use that in just a moment. N would be grams, the way we're going to do these problems. So N would stand for number of grams. Some other helpful data that the person who made this problem set up put up here is this information that a calorie is 4.184 joules. Of course, you know, kilojoule means 1,000 joules, and so on. This table lists some specific heats for different substances, really just for water and gold. But notice that water has a different specific heat in the solid phase than it does in the gas phase, which is different from the liquid phase. And the phase change values, this is heat of fusion and heat of vaporization. I'm going to go ahead and show you how to convert those into joules per gram because I think it'll be useful for us later. So let's make that conversion now. So if I have 6.01, and that's kilojoules per mole, and I wanted to change that into joules per gram, I would put kilojoules down here, and I'd put joules here. Then if I wanted to get rid of moles, I could put moles on top and grams on the bottom. So now we're ready for the relationship part of the conversion. You'd have 6.01 joules multiplied, well, first of all you have to say how many joules are in a kilojoule. So you know, kilo is a bigger thing, and in 1 kilo thing there was 1,000 things going back to August. So 1,000 joules is 1 kilojoule. And a mole, this is water. So for water, 1 mole of water is 18 grams. So then you pull out a calculator. And doing our calculation, we know that we can say 6.01 times 1,000 times 1, I just leave that off, then divided by 18 is 300, we'll just call that 334. So 334 joules per gram. You see kilojoules canceled, moles canceled like that. You have joules and grams left. So that's the heat of fusion of water. For heat of vaporization, you use a similar technique. What I'm doing is doing the 40.7 kilojoules per mole. So you take your 40.7 kilojoules per mole. You want to get rid of kilojoules again. Go to joules. You want moles on top so they cancel. Grams on the bottom, and the relationships are the same. So if it's 1,000 joules is 1 kilojoule, and 1 mole is 18 grams. So you have 40.7 times 1,000, and then divide by 18. So you get 2261. And I'll just use 3 significant digits on that also and call it 2260 joules per gram. So these are the heat of fusion and heat of vaporization values that we will use in these problems. All right, now we're going to go down to problem number 1. And you notice that we have here some chemical reactions and some delta H's. Delta H means change in heat. And then two words. We're supposed to circle the one that's correct, and I'm just going to tell you which one's correct as we talk about this. So endothermic means energy going into a process, and exothermic means energy coming out of the process. Like exit means to go out, so exo means to go out. Exotherm means energy going out or heat going out, flowing out. So in this reaction, since the sign on the change in heat is negative, negative means loss, so a negative sign means energy go out. Energy goes out. So this reaction would be exothermic based on the negative sign that we see right there. Whoops, right there. No, right. It's right here in this number. All right, so the negative sign means energy out. Here, you don't have a negative sign, so that means energy in. So that would be endothermic. And this one, they left it off, so I'm going to just skip that one. And down here, you can see a sign. It's a positive 367.5. So we would say that is endothermic, but energy is going in. So bottom line for this whole question, if you have a negative sign on the energy change, then that means energy goes out. If you have a positive sign on energy change, energy goes in. All right, so now the first question we're going to do. I'm going to do number 3 first. So number 3, we have 25 grams of water at 100 degrees, and we want to see how much heat is removed when it condenses. So here's number 3. Since we're looking at the boiling point, would you use vaporization or fusion? So if you go back to the graph that I made the other day, at boiling, we have this formula. Oh. All right, there we go. So boiling, we have this formula, and for melting, we had this formula. Q is equal to MHF, and Q is equal to MHV. So since we're at boiling, we're going to use the Q equals MHV. Again, how do we know, MHV. How do we know we're at boiling? Because it says you're condensing it at 100 degrees. 100 degrees was the temperature at the boiling point. So the mass was 25 grams. We calculated the heat of vaporization as 2,260 joules per gram. So we have 25 times 2260. So 56,500. Notice that grams cancel, so you have 56,500 joules. Now, often, since this is a kind of a big number, you'll see these answers expressed in kilojoules. So if you wanted to make it go into kilojoules, you just do 1 kilojoules, 1,000 joules. 56,500 divided by 1,000 is 56.5 kilojoules. Now, would that be an endothermic or exothermic process? Well, it says in our question that you're condensing and you're removing heat. So when something condenses, you'd say energy is released because heat is being removed, which, by the way, is why it's more dangerous to get burned by steam than it is by hot water. So if you put your hand in right here, the temperature, if this is a bowl of water and you put your hand in it while it's boiling, the temperature is 100 degrees. But if you put your hand in over here, the temperature is still 100 degrees, but it's steam at 100 degrees, not water at 100 degrees like it is over here. So if it's steam at 100 degrees, all of the energy that it took to vaporize the water is now going to come out into your hand because your hand is colder than 100. So the temperature, the steam would condense on your hand, and that would release not only the energy that's associated with water being at 100 degrees, but it would also release all of the energy that it took to boil the water back into your hand. So it would burn a lot worse if you got burned by steam than it would by hot water. Okay, so we did our final answer on number 3. Now we're going to do number 4. Number 4 is how much heat in kilojoules does it take to heat 200 grams of water from 25 to 100. So if you look at this graph, 100's up here, 25 would be right in this area. So to go from 25 to 100, we're looking at about a 75-degree change. All right, so we're going to have our formula that involves delta T. So if you go back up here, it's this formula. So number 4, Q is equal to M Cp delta T. We know that our mass is 200 grams. And once again, I'm doing this one down here. So I can highlight it. We know that the Cp of water is 4.18. It tells us up here, 4.184. I'm just going to call it 4.18. Now, 4.18 joules is what it takes to raise 1 gram 1 degree. It's also 1 calorie. So 4.18 joules is the same thing as 1 calorie. And then the change in temperature a minute ago I showed you was 75 degrees C, and we get that by saying 100 minus 25 gives us a change, 25, gives us a change of 75. All right, so now if we multiply these 3 numbers together, 200 times 4.18 times 75, 62,700. See, grams cancel, degrees C cancels, and so you end up with joules. But that's a kind of a big number, so we put it in kilojoules. 1 kilojoule, 1,000 joules. So it's 62.7 kilojoules. All right, now would that be a positive or negative sign? We're heating it from 25 to 100, so you're having to put energy in to do that. So that's a positive 62.7. That would be endothermic. Now, if we want to know number 5, we want to know how much energy in calories is removed when you do the cooling from 100 to 25. So notice that this is energy going in because we're heating it from 25 to 100. Now we're coming out. So how would the energies compare? Well, they'd be the same. So you got 200 grams, you got 200 grams, you got a 75-degree change, you got a 75-degree change. The energy is the same. The difference is the energy in number 4 was energy being put in, and in number 5 is energy coming out. So that would be exothermic. So you'd have it's really a negative 62.7 kilojoules, or I'll go back to 62,700 joules. Okay, this is number 5. So this is joules coming out. So really that's a negative 62,700. At the top of this page, it told us that 1 calorie is 4.18 joules. So we'll just make that change. Joules, calories, 1 calorie, 4.18 joules. Does it ask for, it asks just in small c calories, so this will give us our final answer for number 5. So 62,700 divided by 4.18 equals, whoops, didn't have my calculator active. So take that number 62,700 divided by 4.18 equals 15,000. So that's 15,000 calories. That's little c calories. Remember, food calories are big C calories, so it's 15 food calorie or 15,000 regular calories. And again, that would be energy out. So we put a negative sign in front. I'm not going to be real picky about the negative signs, but I want you to know that negative means energy out and positive means energy in. All right, we're going to take a look at number 2 now that I skipped earlier. So let's come back to number 2. All right, in number 2 we have, we're boiling 25 grams of ethanol at 78.5, which happens to be the boiling point of ethanol. So it's 78.5. 78.5 is the boiling point. And the heat of vaporization is 43.5. So for ethanol, if this graph would apply, but the temperatures would be different at which it boils. So the flat line would be down here around 78.5. So let's go ahead and do that. We're at the boiling point. We have 25 grams. We know that the quantity of heat would equal the mass times the heat of vaporization. And the mass is 25 grams. Tells us right there in problem number 2, right here, 25 grams. Then the 78.5 is not relevant except that it tells us what temperature, so we know we're at the boiling point. Okay, the heat of vaporization is 43.5 kilojoules per mole. And it doesn't ask us how much heat. We could give it in kilojoules or give it in joules. Let's go ahead and we'll do it in joules. So we'll take our 43.5 kilojoules per mole. We're going to put kilojoules here and joules there. So 1,000 is 1, just like we have done previously. This time, though, we need to cancel moles again, and grams, and 1 mole. But this is ethanol. So ethanol has a chemical formula C2H5OH. C2H5OH. So carbon has a weight of 12, and 12 times 2 is 24. Hydrogen has a weight of 1. 1 times 5 is 5. Oxygen's atomic weight is 16. 16 times 1 is 16, and then of course you got 1 more hydrogen. So now we've got 24 and 5, and then that makes 29, and if I add that 1 it makes 30, and then 30 plus 16 is 46. So that would be 46 grams. So once again, 2 12s is 24, 5 1s is 5, 1 16 is 16, and 1 1 is 1. So if I add them all together, 1 and 16 is 17, plus 5 more is 22. 22 and 24 make 46. So let's go ahead and do the math. 43.5 times 1,000. And then divide that answer by 46. So you get 946. And that would be joules per gram. So now we're home free. Just go down in here. You have joules, you have grams. 946 joules is 1 gram, is what this tells us right here. So now we just say 25 times 946. 23,650 joules. Does that seem like a big number? See, grams cancel. So that's kind of a big number, so we can make it a little more friendly number by putting joules here and kilojoules here, and 1 kilojoule is 1,000 joules. So you could say that the amount of heat was 23.65 or 23.7 if you wanted to round a little bit more, and that would be kilojoules. So the amount of energy needed to boil the ethanol would be 23.7 kilojoules, assuming the ethanol is at its boiling point. All right, so this video is getting kind of long. I'm going to stop, and then I'll do questions 6 and 7 and 8 in a minute. We don't really need to do, I've already shown you these, so we'll skip number 8. We'll just do 6 and 7. And I'll come back with the next video.